In this video, we will talk about simple harmonic motion. We will first define simple harmonic motion, and we will explain how coordinates, speed or velocity, and acceleration of an object executing simple harmonic motion change with time. We will also introduce crucial parameters in simple harmonic motion, such as amplitude, frequency, angular frequency, and period of the motion. Finally, we will solve a few problems based on these concepts. Simple harmonic motion is defined as periodic motion that is sinusoidal function of time t. There are two sinusoidal functions that we usually use here. The first one is cosine function of time and sine function of time. So these are the trigonometrical cosine and sine functions. Now we note that the argument of a cosine or argument of sine must be unitless. That means we usually multiply a parameter with time. Let's call that parameter now omega. We will explain the significance of omega in a few minutes, but for now this is how we write sinusoidal functions of time for an object executing simple harmonic motion. A quick comment about this product omega t. This product omega t is unitless. So that means the dimension of omega must be inverse time. Let's briefly describe simple harmonic motion. If you have an object right there which begins to move from x equals to 0 point, right there, it starts to move first to the right all the way until it gets to x equals to a. That is the maximum x coordinate it will get to. After that, it will come to rest, and then it will reverse its direction, like that. Now it will move to the left, passing through x equals to 0, and all the way to x equals to minus a, at which point it comes to a complete rest. And then it reverses its direction of motion, moving back to the right, passing through x equals to 0, all the way to x equals to a. And it comes to rest, reverses its direction, and then moving back all the way to the left until x equals to minus a, and then reverses its direction again, and so on and so forth. So when this back and forth motion happens indefinitely in time, we say this object right there is executing simple harmonic motion along the x-axis between x equals to minus a and x equals to a. The change of this object's x-coordinate as it moves back and forth can be written in the following manner. A cosine omega t plus a constant phi. Now this a here, these 2 points, are known as the amplitude of this motion. So that represents the biggest or the maximum displacement of this object from x equals to 0. And it has an SI unit of meters. Omega is known as the angular frequency of the simple harmonic motion, with the unit of a radian per second. What about this phase constant phi? The value of this phase constant can be determined if we know where the object is at t equals to 0. So let's say in this example, at t equals to 0, the object is at the origin. Then by substituting this information in here, we see that the left-hand side is 0 when t is 0. So that means cosine phi is 0. And phi can be taken to be plus minus 90 degrees, pi over 2 radiant. Which means after you substitute this inside here, you can rewrite the coordinate as plus minus a sine omega t. Now let's assume at t equals to 0, the object is here. so x equals to a. Substituting this information in this expression, you get a equals a cosine phi. So cosine phi is 1. That means phi is 0 degrees. So substituting 0 in here, you see that in this case, the expression for the variation of coordinate for this particular simple harmonic motion can be quite simply written as a cosine omega t. So now you see how both cosine and sine functions can be used to represent a simple harmonic motion. The type of force that produces simple harmonic motion is called the restoring force. An example of a restoring force is the spring force that we have seen in one of our previous videos. In this case, if you have a mass, let's call that mass m, it is connected to a spring with spring constant k, and the mass is going that way. The spring will pull it in an opposite direction to restore its original condition, and vice versa. So from Newton's second law, when such an object is acted upon by a spring force of this nature, we know that that force equals to mass times acceleration. So since the coordinate of this mass changes with time, the acceleration changes with time in general. And we can write the coordinate of such a mass as a function of time in a following manner: minus m over k times the acceleration as a function of time. But we also know the acceleration can be written as the second time derivative of the coordinate, like that. So if we ask a question, what function x that would satisfy this equation, that when you differentiate it 2 times with respect to its argument, you get back the same function with a negative sign? Now, there are only 2 candidates. The first candidate is cosine function. Let's substitute this into this equation and see what happens. The left-hand side is substituted for x. Differentiating this function first time with respect to t will give you minus a omega sine omega t. And when you differentiate again with respect to time, you get minus a omega squared cosine omega t, which can be put in here. Now comparing the left-hand side and the right-hand side, you can cancel a cosine omega t like that, and you see that you end up with m over k omega squared equals to 1. Now that means your omega, which we had identified earlier as angular frequency, can be written in terms of the physical properties of the simple harmonic oscillator. So this is the spring constant of the spring, and this is the mass that is executing simple harmonic motion. So what we have shown is that if you have such a system that is connected to a spring, and you pull it to the left or to the right and let it go, this object here will execute simple harmonic motion. And spring force is one example of a restoring force that can actually produce such a motion with an angular frequency given by this expression. In addition to angular frequency, there is another frequency that we can define, so-called linear frequency, and it's related to angular frequency in a following manner. Angular frequency divided by 2 pi. And the unit for this f is hertz, or quite simply 1 over second, as opposed to radian per second for angular frequency. And one other parameter that we can define for simple harmonic motion is period. So period is defined as inverse frequency, and obviously it has an SI unit of seconds. So what is period? Period is time for an object to go one complete cycle. Let's say it starts at x equals to 0, it goes all the way to 1 amplitude, goes back, and then come back to x equals to 0. So that full amount of time is called the period of that simple harmonic motion. Now let's define velocity and acceleration for simple harmonic motion. Let's say the coordinate of an object executing a simple harmonic motion is given by the following expression, sine omega t. So how do we determine its speed as a function of time? Now we know speed can be defined as the time derivative of the coordinate. So if you take the derivative of that function with respect to time, you get a omega cosine omega t. And to get the acceleration, all you have to do is to take the time derivative of the speed that we have just derived. So that's going to give you a minus a omega squared sine omega t. This is called the maximum speed of this oscillator, and this is called the maximum acceleration of the oscillator. Let's do a problem. A mass 600 grams is fastened to a spring with spring constant 70 newtons per meter. The mass is displaced 10 cm from the equilibrium position at x equals to 0 and released at t equals to 0 seconds. So that means at t equals to 0 seconds, the position is the origin x equals to 0. Assume the system is frictionless. Calculate the simple harmonic motion's angular frequency, system's frequency, and period. What is the maximum speed and acceleration of the mass? And where is the mass located when it has this maximum speed? Let's calculate the angular speed. The angular speed is defined as the square root of spring constant over mass. Since the spring constant is given, is 70, the mass is 600 grams, so you have to convert that into kg. And when you do that, you end up with a value of 10.8 radian per second for the angular frequency. Now the linear frequency, or the system's frequency, is given by omega over 2 pi. Now since omega is 10.8, and take that, divide that by 2 pi, you will get 1.72 hertz. Now the period. The period is simply the inverse of frequency, and since frequency is 1.72 hertz, inverse of that will give you 0.581 seconds. Now the maximum speed. Now note, the maximum speed is given by the product of amplitude times the angular frequency. Now we know the amplitude for this simple harmonic motion. The amplitude is given by 10 centimeters because the mass is displaced 10 centimeters from the equilibrium position and it's released. So that means the amplitude is 10 centimeters. In meter is 0.1. Omega is 10.8. So that means the maximum speed is 1.08 meter per second. Now maximum acceleration. The maximum acceleration is given by amplitude times the square of the angular frequency. Now we are computing the magnitude of the maximum acceleration. So again, the amplitude is 0.1. Omega is 10.8. Square that, which is about 11.7 meter per second squared. So where's the mass located when it has maximum speed? Note that the expression for its coordinate can be written in the following manner using the sine function, because we know at t equals to 0, x equals to 0, so we have to use sine and not cosine. Its speed is the time derivative of x, so that's going to be a omega cosine omega t. And the acceleration is the time derivative of v, and that's going to give you minus a omega squared sine omega t. When v is maximum, a has got to be 0, and that happens when omega t has following values. It can be 0, it can be pi, it can be 2 pi, and so on. So when you substitute any of these values inside here, you will see that x will also be 0. So that means the mass is located at x equals to 0 when it has this maximum speed. Thank you for watching.